Okay, I'm coming from an engineering group at UC Santa Barbara. Everything that we think about in my group has to do with kinetics, we work on many different aspects of kinetics. I have several people in the research group who think about solute precipitate nucleation. This is sort of a new area in contrast to a lot of the work that had been done prior to our work was all on single component nucleation systems, things like Lennard-Jones fluids and ice and hard spheres. We began thinking about a solute and a solvent. Brian Goldsmith, one of your tutors here this week, is one of a couple of students in my group working on catalysis, and they think about catalysis on amorphous materials. Again, this is a little bit of a different twist from things that have been heavily studied by theorists in the past, looking at metal oxides and metal surfaces that are crystalline. There are a number of new challenges that you encounter in these areas, and we also occasionally do sort of very engineering applied kind of things, thinking about what's happening in a reactor or a crystallizer at the macroscopic scale. I regard that stuff as kind of important, even though probably it's very boring to this audience. There are processes like heat transfer and mass transfer that can make a big difference in between what you measure and what's actually happening at the molecular level. Sometimes people think that they're measuring something that reflects intrinsic kinetics, and actually there's some other processes between that molecular scale and the measurement scale that intervene and change the outcome of that measurement. So I sort of think of it as part of the requirement of being a card-carrying engineer that we should be able to keep this tradition alive and be able to quantify those kinds of effects. So the part of the group that I'm going to tell you about today is really, in some ways, kind of the smallest part of the group. I only have really one graduate student who's been doing a lot of work in this area, and he's not here. But nevertheless, we have thought a lot about this over the last few years, and I think we've managed to maintain a little presence in this area. And I will tell you about some rather unique things that we've done to try and discover what are the right reaction coordinates. So why theory and computation? I probably don't even need to have this slide in this audience. All of you know very well that the two main goals that most people would cite if you ask them why do you do theory and computational work are that we want to be able to make quantitative predictions so that we can design better materials, better drugs, better solvents, better catalysts, those kinds of things. And we also want to be able to use computational methods to be able to extract some mechanistic understanding at the molecular level of the kinds of measurements that we're making macroscopically. Okay, so I think that one of the prime examples where this has really had a huge impact is the area of catalysis. So people have known about Sabatier's principle and volcano plots for a long time. You see one here from 1961. But what has recently emerged is that you can actually use computational methods, things that people in this audience are probably much better than myself at doing, looking at the elementary steps that happen on the surface and be able to find descriptors, in fact, that correlate very well with this axis. And that is a very useful way of discovering not just the metals that you can easily prepare and measure their rates, but also alloys that have never been prepared. And actually, some new catalysts have actually been discovered this way that are very cheap, and yet they live at the top of this volcano curve. Okay, so this is really a nice example where computational methods and theory have been able to make predictions about new materials and to really be able to extract mechanistic understanding for all those elementary steps that are responsible for the overall rate laws that are observed. So one of the sort of drawbacks of working in that area, as a person who doesn't think about the electronic structure theory problems themselves, I think that's where most of the real challenges still lie in that area. Theoretically, we have sort of a standard toolbox for attacking those kinds of problems. If you're working with chemical reactions that are breaking one bond, forming another one, maybe there are many steps in an overall mechanism, but each of them can be described using a transition state theory framework, or perhaps if you're doing gas phase chemistry, you might need to use our KM theory framework instead. But in both cases, there are established transition state search algorithms that work pretty well, things that you already heard about this week, like nudged elastic band and the dimer method, for example. And there are established ways of using the outputs of those transition state search algorithms in these theories, and perhaps you need some corrections for tunneling and recrossing. But more or less, we know how to solve these kinds of problems. And they are the key thing that makes them solvable is that when you think about the bonds that are breaking and the bonds that are forming, the atoms that are involved in those processes only have to move a few angstroms, and the bond's broken and a new one is formed, right? So in between, along that trajectory, as they're going through that bottleneck region, there's really no obstacle. The landscape looks smooth on that length scale. And so your atoms are moving here only by a few angstroms and going along this path. The energy landscape looks smooth on that scale. Okay, and that's what allows you to use the ballistic framework of transition state theory that says trajectories cross through this dividing surface and they never recross. They're going to make it all the way over here to what is the chemisorbed state in this little diagram. And that's really what has enabled so much progress, right? So if you can find this point, you can characterize this entire bottleneck region and its dynamics very well, right? And that's actually been the revelation that goes all the way back to 1935. Wigner and Eyring said that the entire rate basically depends on the landscape near the vicinity of this bottleneck. Okay, now there are a lot of other problems where that doesn't happen, right? So problems like this, like if you think about protein folding, reactions in solution where the solvent is actually a player in the reaction coordinate, things like electron transfer or things like nucleation, what defines the reactant and the product and the way they differ is not any one specific molecular degree of freedom or one specific bond. It is instead a whole bunch of degrees of freedom, a whole bunch of native contacts, solvent coordination shells in these two cases, nucleus size and all of the atoms that are belonging to the nucleus and the ones that are out here in solution still have something to do with, basically this nucleus has to reach a critical size in order to be stable, right? So each of these is defined not in terms of 1 or 2 degrees of freedom, but instead in terms of hundreds or even thousands of degrees of freedom, right? And no one degree of freedom is more important than the others, and that's sort of the nature of the problem. Problems like this are associated with what we call rugged energy landscapes. And what sense is the landscape rugged? It's that if I start with a trajectory and I look at the path that it takes going from all the way from one stable state over to another one, it traverses many little bumps on the energy landscape, right? So those might correspond to very unimportant things like one solvent molecule slipping past another one in solution, right? So each one of those little events is associated with a little bump on this energy landscape. This is a figure, by the way, borrowed from the review article by Christophe Delago. I should give him credit for that, and I forgot to. Anyway, so the point is that there are lots of saddle points here, but none of them is of any consequence in terms of the overall progress towards the reactant or product. They're all basically irrelevant, as opposed to this case where you have just one saddle point that really defines the boundary between A and B. Okay, so what we do know, though, is if we start with a problem like this that has this rugged energy landscape, we can, if Rudy Marcus is available to tell us what is the right reaction coordinate, he told us that we should use the diabatic energy gap between the two diabatic states in this problem, then if you project the free energy landscape onto that energy gap reaction coordinate, you recover something that's nice and smooth again and that you can make sense of. It has just a couple of key parameters that are important in the problem that emerge after doing that free energy calculation. And again, if you know the right reaction coordinate, you have some very standard tools that allow you to do these kinds of calculations, right? So we have umbrella sampling that's now 40 years old, and metadynamics is much newer but does basically the same thing. So you can take the coordinate and compute the free energy as a function of that coordinate, and that works great, except for one caveat that we've known a long time, even from before we could actually compute these free energy surfaces. Theorists recognized that if you knew the free energy surface, it would only tell you about the kinetics if you used the correct coordinate, right? So this goes back to the variational theory of transition states. And what we know is that if you use the wrong coordinate, you will get wrong rates out, right? So you'll get a free energy landscape. It'll look perfectly fine, but it doesn't actually tell you anything about the kinetics because it's not in the correct direction to describe the appropriate collective degrees of freedom that are happening that take you from one state to the other, okay? So this is a very important thing to realize. Now what I want to do is to focus on these cases over here on the left, and I've grayed out these over here. These are things where we really don't even know how to get started on this side. But if I just look at these 4 examples, an example where you might apply transition state theory, and an example where you might apply RKM theory, and an example where you might apply electron transfer theory, and one where you might apply, say, classical nucleation theory. these, I would argue, these four theories are the four most successful rate theories that exist today, right? So what do they all have in common? I want to sort of start out with a little motivating quiz for some of the things that I will ask you. So I will give you one example of something that makes these four theories special relative to the various computational frameworks and other theories that you might have seen in the literature. Okay? So one of the things that makes them special is that they address not just one nucleation process or one particular electron transfer process or one gas phase reaction or one particular chemical reaction. They address entire classes of phenomena, right? So that is actually an extremely powerful thing, right? So they address entire classes of phenomena. I'll let you guys continue. What is another thing that is very special about them? Somebody not from my group. Nobody can think of anything particularly special about these theories. Okay, you want me to give you another one? Another example of something that's special about these theories. They predict trends, right? Every one of these theories predicts not just a number, the rate is this at this condition. It also predicts trends and how the rate depends on physically important parameters in the problem. Right? So that's one of the things that you see here. For example, if you look at the transition state theory equation, you all have probably seen that if you multiply by h and divide by kb over t, or by kb times temperature, then you take the log of that and you get what's called an Eyring plot. If you plot that versus 1 over RT, right, you get an Eyring plot. And we know that the Eyring plot identifies for you from the slope, it identifies the activation enthalpy, and from the intercept, it identifies for you the activation entropy, right? So these are two physically meaningful parameters. Every one of these theories is based on just a couple of physically meaningful parameters in the problem, right? So in nucleation theory, you have a prefactor and a parameter that's related to interfacial free energy. That's this nucleation barrier parameter. Over here, you have the driving force and the reorganization energy that are important for electron transfer. And here you have two properties of the density of states that are important in the RRKM theory. Okay, so these are theories that are very, very general. And in a sense, they're general because they're based on these physical parameters that are important for the entire class of phenomena that they describe, right? So that actually has an implication that I think is really important. It means that I can look at these theories and I can make predictions about what will happen when I make a little change to the temperature, or because for example, this parameter tells me something about the interfacial free energy of the problem, I can make predictions about what will happen if I make a little change to the solvent, and that will change the interfacial free energy between my nucleus and the surrounding solution, right? So all of these things make predictions like that, and that I think is particularly valuable. It is, in a sense, why, so this is an audience full of simulators and computational people, and what I'm going to say is potentially going to get me hurt, but simulations and computational methods are no substitute for a good theory, right? So we should always keep in mind that, if we can achieve something like this, if we can get to this level, then you have something really, really, really powerful, right? Because if I want to, say, use forward flux sampling, which is a really, really beautiful and wonderful method to compute the rate of some process with a large-scale parallel simulation, right? And then somebody asks me, okay, what if I change the composition of the solvent just a little bit? What if I change the temperature just a little bit? What is the rate going to do? The only way to answer that question with forward flux sampling, Markov state models, all of these methods where you use the trajectories first and then ask questions about trends later, is to rerun the simulation at the new condition, right? So what's special about these kinds of frameworks is that they can tell you how the system is going to respond to changes based on properties of the transition state ensemble in these kinds of, that are really embedded in the definitions of these kinds of parameters, okay? So hopefully that is clear. I think it's a particularly important thing. So let me now turn it over to you guys again. Something else that's very special and unique about these four theories that I think you probably can't say about very many computational frameworks. Nobody's gonna offer up anything. What can you do with these kinds of frameworks that you really nobody ever does with a computational method?
Well, they are analytical expressions. I can manipulate them.
Yes, you can manipulate them and use them to analyze data, right? I mean, you can use them in reverse, right? So computationally, I can set out with a method and I can make predictions about the rate, for example. I can make the same predictions about the rate that is embodied in every one of these numbers, right? But what I can't do is take somebody's experiment and fit the data and extract the parameters directly from the data, right? So these expressions are really powerful, not only because they allow you, if you have a way of computationally predicting the values of these parameters that go into them, you can predict rates, but you can also abandon the computer entirely, take somebody's experimental measurements, and you can extract parameters that tell you something about the underlying molecular physics without doing any computation at all. And I think that that's yet another example to show you that the theoretical framework itself, these simple theoretical frameworks that boil things down to the very, very simplest minimal description involving just a few important physical parameters, is really valuable, right? Now, there's a fourth thing that these theories have in common that really motivates the rest of the talk. And this one, the last one is just there. It's there on the slide. What is special about all four of these theories that have really been the driving force behind all rate theory work that I think really matters? No, you can't answer, obviously. You're one of my graduate students. What's written there on every one of them? Every one of them, the pioneers behind these things, specified a physical definition of a reaction coordinate, right? And that is what makes it possible to do all of this analysis, right? That's what makes it possible to take these phenomena, which all involve hundreds, thousands of atoms, and boil it down into a very simple physical picture based on a free energy barrier or a prefactor, is that if you know the nature of the reaction coordinate, it's possible to do this dimensionality reduction and take this incredibly complicated process and put it into very simple terms and actually identify the physically important parameters that govern the rates and all the trends associated with the phenomena, right? So it's really the fact, in my view, it's the fact that every one of these theories, so Gibbs told us we should think about nucleus size, Marcus told us we should think about energy gaps, and Eyring and Wigner told us we should think about unstable modes at the transition stage, right? So in every case, there's a physical definition of this reaction coordinate. I want to emphasize again, it's physical. It's not an abstract thing. It's something you can actually go out and compute its value and compute and design computational methods around actually computing nucleus size, energy gaps, and saddle points and find these unstable modes, okay? So these are things that we can actually put into practice, and they are things that we can actually use to build theories that we can use in reverse to analyze data, right? So that's I think the sort of setup behind this talk. Now there are a few problems that I had on the previous slide over here, things like this, where we actually still don't know what the reaction coordinates are for those kinds of problems, right? And if we did, I would argue that we could probably make the same kinds of impact in thinking about reactions in solution and biomolecular conformational transitions and things of this sort, right? So there are many examples of problems where some genius has not actually given us the answer to make this nice simple picture yet. And yet there are a couple of cases where it is possible to go from here to a nice simple picture based on just a few parameters. Okay, so there's hope for doing this, and I will try to show you in the talk that I think we're making progress in being able to actually do it in practice using some new computational algorithms that actually use the computer in a sense to tell us what we should be computing. That is, we should be computing free energies along a specific coordinate that the computer identifies for us, and that's what I will tell you about today. Okay, so this I think is just to say that if we could find the reaction coordinate, that we could use Cramer's theory, we could use mean first passage time theories, The only reason that we can't use these things is because no one has told us yet what is the reaction coordinate yet, right? So these things would be transformed from being sort of fancy mathematical frameworks into something useful if we could just figure out what to plug into them. And so there are sort of two philosophies in the field of rare events these days. One of them says, you can design methods, and they're very, very powerful methods, that will actually give you the rate even though you don't know the reaction coordinate, right? Those are transition path sampling, transition interface sampling, forward flux sampling, Markov state models. All of these kinds of methods allow you to do this. But I would argue that if we can instead design methods that find the reaction coordinate for us, then we can go out and we can use these. We can, of course, go back and get the rates too, but we have all the insight that comes along with having these nice, simple theories like this, okay? So that's the motivation for the rest of the talk. Now, the tool that I'm going to use to discover reaction coordinates really rests upon some formalism that doesn't bias the sampling along any particular coordinate. And the one method that allows you to do that is transition path sampling. So when transition path sampling came out back in the late 90s, people were very excited about this method. Effectively, transition path sampling is for dynamics what Metropolis Monte Carlo is for instantaneous properties, right? So that's a very bold statement, but I think it's absolutely quantitatively true. In Metropolis Monte Carlo, we take configurations, we modify them, and we accept or reject them according to a detailed balance criteria. And you can prove that if you have an ergodic set of moves, that you're actually generating the equilibrium Boltzmann distribution, right? We can set up the same framework with dynamical paths, right? And the way it works, we come up with procedures for changing one path into another one. So you start out with one path, you do what's called a shooting or a shifting move, and that changes the old path into a new path. You have a detailed balance criteria that assigns weights to different paths according to their probability of being observed in the dynamical phase space. This is the space of paths. So that space, I'm not going to spend too much time talking about transition path sampling, but you can think about how it's formulated in the following sense. Every path has an initial condition, and that's drawn from the Boltzmann distribution. And every path has a probability of moving along a specific trajectory given that initial condition. And if you have a thermostat, that's going to be a probability distribution. If you have deterministic dynamics, it's entirely determined by your initial condition. Okay? So this is how you write down what the path weights are. Once you know the relative path weights between two paths, you have the detailed balance criteria, and then you can design acceptance rules that allow you to decide whether to accept changes that you've made in these paths. Okay? So everything works analogously to Metropolis Monte Carlo, except that we're not sampling configurations, we're sampling dynamical paths. And that allows us to compute averages in the same way that we use Metropolis Monte Carlo to compute static averages. We can now compute averages of rare dynamical things that happen, like going from a reactant state to a product state when there's a big barrier between. Okay? So this is the basic idea behind transition path sampling. Very, very powerful idea. Review articles were written by Americans that called it the Cadillac of reaction dynamics methods. Review articles were written by Europeans that called it the Rolls-Royce of reaction dynamics methods. And so it generated a lot of excitement. But then reality set in, and people encountered some very practical issues. So Don Frankel in 2005 wrote that transition path sampling is inefficient for processes that take longer than a picosecond. And I think that Dan was actually being somewhat gentle in this statement. What happens is with the old methods is that the efficiency just plummets to zero, basically. You stop getting any accepted paths if you have long transition paths. Now, remember the smooth versus rugged energy landscape setup, right? So you have what makes a transition path long is when the energy landscape is rugged. The system, that time associated with the transition path is the time to fall off the top of the barrier. If it's diffusing around on a rugged energy landscape, that takes a long time. If it's a ballistic motion, it comes down very fast in tens, hundreds of femtoseconds, right? So basically, what's highlighted here is a real serious problem. It's exactly where transition path sampling would potentially do something that nudged elastic band cannot, that transition path sampling stops working, right? This is with the old transition path sampling methods. Okay, so this was really a problem, and I think that because of this, many people developed a sort of 2000 year 2000 level technology view of transition path sampling that stuck, and they said, well, this only works for toy problems, and it's not really an efficient method for real things. I will show you that we can fix this problem, fix it by many orders of magnitude, so that it's actually not a problem in efficiency at all anymore. There are other problems associated with the sort of underpinnings. What transition path sampling was designed to do is to compute rates when you didn't know the reaction coordinate. But then, of course, what people want is the reaction coordinate because it comes along with all of this mechanistic insight that I already highlighted, right? And what Chandler pointed out himself in 2004 is that really they have to just try coordinates and check to see whether they're correct. There's no systematic way of going about discovering what the correct coordinate is. And the problem with trial and error in this case is that every time you test a coordinate, you usually find out that your guess was wrong, and each test is extremely expensive, right? So two more problems here pop up in transition path sampling that make it sort of practically limited. Sorry, I will try to stop walking in front of you. OK, so aimless shooting is a version of transition path sampling that we developed to get around some of these efficiency problems. I won't say very much about the actual algorithmic details. I think that stuff is probably best learned from going to the papers anyway. But what I will say is that it's actually tremendously easier to implement than the original shooting and shifting procedure. I mean, I am computer disabled by many measures. My students will attest to that. And even I was able to write the code to do this, right? So this is a nucleation problem, sort of prototypical problem with a rugged energy landscape. It doesn't matter who joins the nucleus. There's this rugged energy landscape associated with moving anyone through this sea of solvent molecules. And what you see here is that we were able to sample trajectories that were 400 picoseconds long in duration, and we still got 30% acceptance, right? So, which is really good. Anything in the order of 50% acceptance is great for any Monte Carlo type algorithms. The same goes true for transition path sampling. And so this is exciting because remember, Frenkel had said that as of 2005, TPS was inefficient for processes that took longer than a picosecond. So we're really pushing out another 2 or 3 orders of magnitude in our ability to sample these kinds of things. And I would argue that the only reason we can't go longer is because sampling 3,000 trajectories that are each hundreds of picoseconds long is just more computing resources than we have access to. But it's really not a matter of sampling efficiency now. So the underlying algorithm can actually do this now without any problem. So aimless shooting fixes this problem. I should note in fairness to others that there are a few other examples of algorithms now that can actually also correct this problem. And you can read about those. I have a review article in Molecular Physics that goes through some of those kinds of algorithms. So there are still the problems with identifying and validating the reaction coordinates. And that's really what the rest of this talk is going to be about. Okay, so just to motivate this talk one more time, this is a book on reaction engineering written by 2 experimentalists. And you see what they think of us theorists. They say the words mechanism and model have acquired bad connotations because they're associated with much speculation, right? So this is something that we really don't want to do, right? We don't want to toss around the word mechanism in a hand-waving sense, because I think that really when we spot something in a movie and we think in a simulation movie and we think, okay, that's the important degree of freedom, and we write an entire story or an entire paper around that being the mechanism of the process, then I think what we should be able to say and trust is that if we integrated out the rest of the degrees of freedom, that one degree of freedom would still give me a free energy landscape from which I could compute rates that were accurate for that model chemistry, right? And I think that in many cases people aren't quite so stringent with using the word mechanism, and that's really, I think, what is being referred to here. So what are the kinds of things that I mean by having the reaction coordinate and the kind of mechanistic insight that you can get from it? Well, I already told you that we can do this dramatic dimensionality reduction, that if you have the right reaction coordinate, then the free energy landscape, as a function of that reaction coordinate, will actually reflect the proper thermodynamics and the dynamics. That is to say that it's the one that actually controls the rate of passage from this state to that state. It gives you an accurate summary of the transition state ensemble, and you can use that to do computational work, right? So if you know that this is your reaction coordinate and this is the location along the reaction coordinate that corresponds to the bottleneck, then you can actually imagine doing some umbrella sampling, collecting an ensemble of those transition states, and then using things like thermodynamic perturbation theory to ask, if I make a change to the conditions of my system, composition or temperature, how would the free energy of these transition states change relative to the change in the free energy of my reactants? And that's how you predict those trends using computational approaches, right? So this is something that in principle we should be able to do if we know the right reaction coordinate. We can, of course, test mechanistic hypotheses to the extent that specifying the reaction coordinate is specifying the mechanism. We are testing mechanistic hypotheses that are put forth as opposed to just speculating about them. And this is something that's really new that I'll show you an example about today. If you are preserving the thermodynamics and the dynamics in your dimensionality reduced model, this is exactly what reaction dynamics theories have worked on for many, many decades. And we can actually go back and we can test whether their assumptions are valid and whether their conclusions are valid by actually checking them in large-scale simulations and seeing whether the assumptions made in those theories are actually true. Okay, so the last bit, and this is something that I won't emphasize here, it's been emphasized in many review articles and many papers throughout the literature, is that if you know the correct reaction coordinate, then all of these rare events methods work much more efficiently. It's easier to get free energy barriers and rates if you know the correct coordinate than if you put in the wrong one. You know, there are many methods that will go ahead and give you the right rate anyway, but that comes at a computational cost. If you know the right coordinate, you get the efficiency along with it, right? So you get the insight and the efficiency if you know the right coordinate. Hopefully I've convinced you that reaction coordinates are a worthwhile thing to go and find. Okay, so when I used to give this talk, I used to launch in and tell people all about the how to do it, and then at the end, I got a sense from the questions and from discussions that people thought, well, reaction coordinates are completely unimportant. I'm giving you guys the opposite talk today that tells you why you should want to do this, as opposed to just going out and running a large-scale simulation and getting rates without knowing the reaction coordinate. Okay, so what is the reaction coordinate? Well, it turns out that we know, right? So the reaction coordinate is this committer. Onsager called it a splitting probability. It is, if you wanted to compute it for any particular configuration, so this depicts a high-dimensional potential energy surface with a stable state A and a stable state B and some energy landscape between them. So if I started from a configuration here and I launched a whole bunch of trajectories, the committer would be about 3/4 if 3/4 of those trajectories went to state B before they went to state A. Okay, so this is the statistical definition of the reaction coordinate. It doesn't give you a whole lot of insight, but it does exactly what it's supposed to do. It's a measure of the dynamical progress on the way from state A to B. If I start at the edge of state B, it is perfectly 1. If I start at the edge of state A, it's perfectly 0. And if I'm exactly on the dividing surface between A and B, it's 1/2. Okay, so my transition states are points where the committer, the splitting probability, is equal to 1/2. This thing has a number of advantages. Theoretically, you can do a lot of nice work with it, but it's not the kind of thing that you want to be computing on the fly, right? So if you're looking at a trajectory, you don't want to stop and make a plot of the reaction coordinate as a function of time, which usually we would think is an interesting thing to do. Here you would have to take every point along the trajectory and compute a whole bunch more trajectories to get that plot, right? So this is a very inconvenient object to work with. It just tells you a number. It doesn't give you any real physical insight about what is special about this configuration that made it more like B than A in this high-dimensional landscape. Now, you encounter the same problem if you look at diffusion map methods. In a sense, diffusion maps and reaction and the committer are one and the same. In fact, Noe showed that when the Bayesian definitions are established correctly, that these two things are one-to-one interconvertible. There's actually no difference between the committer and the first eigenfunction diffusion map. Okay? So all of the things that you heard about diffusion maps earlier in the week are really the same things you could say about committers. They are exact reaction coordinates, but they're abstract. It's hard to pull out physical meaning and understanding from those kinds of abstract frameworks. And that's what I'm going to be telling you about how to do, is how we can identify physically meaningful coordinates, something like a bond angle or something like a nucleus size measure or something like that we actually can see, can track with our eye, and compute on the fly and get some insight into what are the important degrees of freedom and what are the unimportant degrees of freedom. Okay, so these physical coordinates, the problem with them is that they can be good or they can be disastrously bad. Okay, so this is the case that shows the way everything is supposed to work. I've got my high-dimensional landscape again in coordinates 1 and 2. If I chose that coordinate 1 was going to be my trial reaction coordinate and took this energy landscape, projected out coordinate 2 to get the free energy as a function of coordinate 1, then I would get a barrier with a peak at location Q1 star. That location, if I were to follow it back up into the original landscape, does correspond to a dividing surface in the correct place, and everything's working the way that it should. Okay? You can also have this situation where I have, again, basins A and B, an energy landscape between them. I'm going to project out coordinate 2. I would get the same double well energy landscape, and maybe I would write a whole paper saying that I've solved this problem and I now understand the mechanism, that it's related to Q1 because the free energy barrier looks the way it's supposed to look. But what happens, if you look back in the original landscape, you see that the dividing surface that corresponds to states with a constant value Q1 star cuts through space like this. And what you see is that it's cutting through the edge of basin A, maybe obliquely crossing through the transition state region, and then cutting through the edge of basin B. Okay? This is not what's supposed to happen, right? So what happens if you compute committers for the points that live on that dividing surface corresponding to this bad reaction coordinate? Well, all those points that cut through the edge of basin A, they have committers near 0. On all these points that cut through the edge of basin B, they have committers near 1. If you make a histogram of a sample of points and their committer values from sampling on this dividing surface, you get a bimodal histogram, and that's a signature of a bad reaction coordinate. Now, you can visually see that things aren't working the way they're supposed to in this problem, but that's because it's a two-dimensional problem. If you're working in 10,000 dimensions, you can't actually see that you've chosen a bad coordinate, and you might think, and many people do, download plugins and run free energy calculations and publish papers saying, without doing any testing to see whether this coordinate is actually the correct one, right? So this is kind of a dangerous thing to do, and you could have this situation lurking underneath, and there wouldn't be any indication that it is if you don't actually perform these kind of diagnostics. Okay, so the problem with this procedure, perfectly valid and rigorous, but all of the trajectories that we computed to get all these committer probabilities, they add up to about 100,000 trajectories using protocols that are published in the literature. Okay, so that's a lot of work, and it's all wasted, right? So if this comes out bimodal, then all the data that you generated was to test this coordinate. Now you want to go back and test a new coordinate, you have to start over again. Another 100,000 trajectories, and experience tells us that if you're guessing, you're probably going to get it wrong the second and third and fourth times too. Okay, so this is why it's a painful procedure to do. So of course, this is what's supposed to happen. You appropriately mix these two coordinates, which are both important in this problem, and you get a isosurface of your trial reaction coordinate that actually coincides nicely with the true dividing surface. And now all the points on this dotted line are actually transition states, and that will mean that this histogram will come out with a single peak near 1/2. Okay, so that's an indication of success. And this is what we would like to happen. Okay, so can this test be made less expensive? So the reason that you would want to make this test less expensive, of course, is that many people over the years kind of abandoned doing this rigorous validation approach and just went back to guessing coordinates and publishing the results. So here is the actual committer distribution. But notice that the way we define the committer is actually a binomial sample of a finite collection of trajectories that either have to go to A or B, right? So this binomial probability distribution convolutes the real underlying committer distribution with the binomial to give you the histogram that you're looking at in the test. And it turns out, this is something I noticed back in 2006, that you can actually undo that convolution process. And you can take a very inexpensive calculation of these binomial sampling probabilities. We don't have to compute hundreds of trajectories. We can get away with 10 or 20 for each configuration that we test, and that'll give us a really ugly looking histogram. But we can actually take the histogram and go backwards and get back to the moments of the underlying distribution. And that's now free of what number we used for the for the binomial convolution process, right? So this allows us to reduce the cost of doing this test by upwards of a factor of 10. And that's I think, really nice because it allows us to do a completely rigorous and equivalent test to validate the coordinates that we're using, but we no longer have this painful, expensive procedure. It now becomes much less expensive than computing the free energy surfaces that people are already computing anyway. And actually, it also becomes quantitative. So it's a completely win-win kind of setup. You can now make quantitative statements that say the real committers are mu plus or minus some standard deviation, and it's not just an eyeball test anymore. Okay, so the test is still very hard to pass, and so it's still quite hard to get people to do this test. I actually had a conversation with a student at a poster once, and I said, why don't you guys ever test your coordinates? And he said, well, we do, but they fail the test, so we just block you as a reviewer. And so, there's still a problem, right? So this allows you to rather inexpensively determine whether or not you have a good coordinate, but it doesn't help guide you to selecting the coordinate that will pass this test. Okay? So that's what so we fixed this problem, and there's still this problem there that needs to be addressed. And that's figuring out a smart way to come about the insights that we need for finding good coordinates. Okay, so this is the idea behind what I used to call likelihood maximization, and I think maybe a more appealing description is that it's high throughput mechanistic hypothesis testing. Okay, so the general hypothesis is that I have this committer. I know that's a good reaction coordinate. I know some coordinate out there exists. And so we're going to propose that it should be possible to find some simple physical variable that adequately describes the outcome of this committer probability, right? So the committer is defined in terms of the full atomistic configuration. But what I'm looking for is a simple physical variable that if I knew the value of that one physical variable, I could predict the outcome of the committer, right? That would effectively collapse this problem from the high-dimensional all-atom description down to a one-dimensional problem. Okay? So how do we go about doing this? We collect data using transition path sampling, using our aimless shooting variety of transition path sampling. That's now quite efficient version of this. And that actually, it turns out that the shooting moves that you do in aimless shooting are unbiased realizations of the committer probability, right? So that's going to form our data set for training a model of the sort of like the machine learning people talk about training sets and test sets. This transition path sampling data that's completely unbiased is going to provide the data set for training our model. Okay? So those are these committer realizations. Now what we're going to do is a data-driven approach. We're going to sit around and brainstorm at a meeting with the students and list all the coordinates that we think might be important in the problem's physics. And then, of course, we have to write codes to compute all those coordinates, and that's where all the work lies. But then the validation procedure is that we're going to be able to go through and we're going to screen all of these. It's going to not only find the best one out of the 100, but it's going to mix and match them in linear and nonlinear combinations to look for things that actually involve multiple coordinates that in complementary ways that you might not have recognized. Okay, so it does all of that automatically. And then after it gives you the best possible coordinate that you can make from the set of basis functions, effectively, that you provided in your trial set, you have to do just one committer test to validate that the best among your trial set was a good one. Okay? Afterwards, what we usually find is that things work pretty well, and we get to do all the things that I advertised that we would be able to do in the beginning of the talk. Okay? So this is a little two-dimensional example illustrating how the method works. This is aimless shooting data. Now, aimless shooting is a transition path sampling method, and so you might have expected to see paths on this slide, but the paths for us are completely unimportant, right? So they're movies of how you go from state A to state B. They're fun to watch, and sometimes they generate some ideas about what coordinates you might want to test. But the actual data that determines the reaction coordinate is in those shooting points. Every time you fire a new trajectory off of an old trajectory, you're flipping the coin once and seeing, did you go to state B, in which case I color it red, or did you go to state A, in which case I color it green. Okay? So that's the test data that you see here. And one of the things about aimless shooting that's really nice, and this is what makes it so efficient, is that it automatically generates the sampling points near the region of the bottleneck of the transition, right? So if you're always firing from a point near the transition states, you always have a high probability of connecting the 2 points on either side, and that's why aimless shooting is so much more efficient than the original versions of transition path sampling, okay? So there you're seeing sort of the visual proof of why this thing works. So then we take this data and we ask, among all of the specific mechanistic hypotheses that we made, what is the best model that collapses the fully atomistic detailed committer onto a crude model of the committer that's phrased like this? So it's the committer now no longer depends on the full x, it just depends on q at that x. Okay, so we've embedded all of that atomistic dependence into a simple function that we can understand. Okay, now we don't know that that's right. In order to tell whether that's right, we have to use a trial function here. This specific form of the trial function is the form motivated by Krummer's theory. It is the form that you should get if you have a parabolic barrier at the top. So it's not a completely ad hoc formula here. And these parameters, as a result of that, have meaning, right? So the A parameter here is one that we're going to optimize as part of the likelihood maximization procedure. And it corresponds to the width of the barrier top. And the Q dagger parameter corresponds to the transition state along your trial coordinate. So this is the best estimate of the transition state location for the trial coordinate that you're looking at right now. Now we have done this for hundreds of trial coordinates and their combinations. And we can now ask, for each one of those trial coordinates that you can create, which one is most likely to have observed this data, okay? So the way that analysis works is that you have the actual outcomes. Some of them went to B, and some of them went to A. There's a probability of going to B, and 1 minus that is the probability of going to A. You plug all of these ones that went to A into this product, plug all the ones that went to B into this product, and that gives you the likelihood that you would have observed the swarm of data colored this way if this model of the reaction coordinate was the right one, right? So then the model that's the best is the one that has the highest likelihood of having generated that data, right? So this is the sort of reverse way of thinking about the problem. We generate the data first, and we try the coordinates second. And that's what makes this approach completely different from the old ways of doing things, is that we're no longer having to throw away data. We've got the data once and for all. We now just have to have the ideas, and we can screen as many ideas as we want from one set of data. Okay? So let's go back to our little Leonard-Jones nucleation problem and see how this works on a real problem. So I got 3,000 trajectories here, a whole bunch of realizations of the committer probability. And now what I'm going to do is to go through the literature from 1981 to 2011. A lot of people have thought about this problem, and they've all had their various different ideas about what coordinates are important for describing nucleation in this system, right? So there are various variations on the Steinhard order parameters here. There are ideas that Parinello has come up with for looking at the average coordination of solid-solid like particles. Lechner and Delago came up with some nice ideas for changing the spatial resolution and getting a tighter structural resolution on these Steinhard order parameters. And there are various combinations of those things that you can make that give you ideas about the size and shape of the cluster. And so let's see how it works. Okay, so it only takes a couple minutes now, instead of months of computing time, to screen all of these mechanistic hypotheses that people have worked on in all these papers. We can do them all in about 5 minutes and take 60 coordinates and all of their linear and nonlinear combinations, and you find that we can actually find a good coordinate. This is a 40,000 degree of freedom system. We've reduced it to 1, and it turns out that it's not a completely alien object. It's a product of a coordinate that Frenkel thought about and a coordinate that Peter Ballhaus had thought about, right? So it turns out that this coordinate is not very good by itself. This coordinate is terrible by itself. But when you combine the two together, they have complementary information, and it works beautifully, right? So they were thinking about the correct things. This is an algorithm now that allows us to rather systematically go through and find the right way of combining different people's ideas and get something that actually works. Okay, so this is the validation. The coordinate is actually correct. It gives you a very tight committer distribution, and we really can be confident that all the points that live along this line, this is my dividing surface predicted by the transition state value of this coordinate, is an isosurface here. So you've got the coordinate Q6 on the vertical axis and N on this axis, so it's sort of these hyperbolic surfaces that run this way. that gives you your dividing surface in this case. And you see that indeed, points over here are colored red. They're always going back and redissolving. Points over here are always growing on and becoming an FCC crystal. Okay? So everything here is working pretty well. And I want to emphasize this point about this being quantitative mechanistic hypothesis testing, right? So every one of these order parameters that's been proposed corresponds to a mechanistic hypothesis, right? So these are the mechanistic hypotheses. This is one that says an order-weighted size. That's the one that we came up with, and it's the best. But granted, we had a tool, and we had all of their ideas to go from, and it really just turns out to be a combination of things they already thought of. This is Frenkel's coordinate, is second best, right? So this was the coordinate that people used from 1996 until our paper came out. This is a coordinate, Steinhardt Q6 coordinates. This is one that people used from, this came out in 1983, and it was really widely used, and people continued to use this coordinate up until our paper came out. And what you can see here, this was really the evidence that I think drove home the point that these are global coordinates. They reflect fluctuations in structure happening throughout the system, and nucleation is a localized phenomenon. It has to do with the emergence of a small cluster of the new phase, not something distributed over the entire box, right? So this coordinate, you can quantitatively see that problem, global versus local order, in the likelihood score, right? So this is 300 e to the 300 times. It's a rather big number based on our data. It's e to the 300 times less likely to be correct for the data that we generated, right? So we can really say there's no way that this is the right thing to do. And now that there's a quantitative answer for this, people have actually stopped doing it. But you can see that it took a long time, right? It's actually, sometimes it takes actual quantitative proof that this is not right to steer people away from a practice that's been going on for 30 years. So this one is the nucleus size coordinate of Tinwald and coworkers. This is actually pretty good. It's only 150 or so log units away from the optimum. This is one by Paranello. It works pretty good. They came up with this because metadynamics has its limitations for running cluster size coordinates, and this one doesn't have those limitations. But you can see here that it's not actually a good coordinate. So sometimes, when you choose the coordinates that you investigate, because of the limitations of the method, for example, metadynamics has to have differentiable coordinates. These cluster size coordinates, they can't work with them. So they came up with different coordinates, but you can see here that their coordinates are not very good, right? So this is, I think, the way we can go through and we can actually quantify the quality of the different coordinates that people are using. And those actually correspond to their mechanistic hypotheses about the way the process happens. OK. So a couple of sort of walk through the different kinds of applications that have been looked at with this. I think that a very reasonable comment that I've heard from colleagues and people in the field is that you'll never find a reaction coordinate for protein folding. And in a sense, I would agree with that statement, right? So it's impossible to imagine that a process that involves so many distinct metastable intermediates can be described by one physical, simple variable that describes them all, right? So the one that describes this transition, for example, is probably different motions than the one that describes going from here to here, right? But there's no reason to really try to do that, right? So if you can construct a Markov state model which tells you how frequently you jump from here to here, but not exactly how you did the jump and what is the bottleneck that sets the frequency of jumping across that point to the value that it takes. If you want to understand that kind of information, we can begin to go in and do likelihood maximization and transition path sampling analysis to figure out what is the actual mechanism and the bottleneck that separates this state in my Markov state model from this one, right? And then we actually can do all the same analysis where you have a simple model that describes each of the individual elementary steps, in a sense, in your Markov state model. And that's what Peter Ballhaus has done here in this calculation. He's found a model that describes the transition actually from this native to this L intermediate in the unfolding of this protein. Okay, so if that's the highest bottleneck along the fastest transition between N and U, then that's actually sufficient, right? So you can know which transition you actually need to do this very detailed analysis on by looking at the frequencies in your Markov state model and then saying, I need to understand this one bottleneck right here in more detail, right? So that I think is a potentially very powerful analysis that does allow us to use some of these tools for things as complex as protein folding. Okay, so one that I'm particularly fond of because this was written by an alumni of my group, Brandon Knott, went to INREL and worked with Greg Beckham on cellulose hydrolysis. And they actually had some really nice work in here. They crystallized the structure of the pre-reactant complex, this mechanistic complex, and they crystallized the structure of cellulose in the enzyme pocket after it's been cleaved. And then they actually used a QMMM simulation to identify, with aimless shooting and likelihood maximization, they were able to identify that these 3 degrees of freedom are actually the important ones in the transition state. And they mixed and matched them and got a description that gives you a sharp, this is the committer distribution, and it's peaked around 1/2. So this is reasonably successful results here. And what I think is really beautiful about this, and this is something that a lot of people have been skeptical about, is that when you find the right reaction coordinate, even for something as complex as an enzyme cutting a polymer, right? This is a cellulose, a polymer to me. For something that complicated, you see here that they get a free energy barrier and they applied transition state theory, and then they check to see if it's a good reaction coordinate. The theory tells me that it should have a high transmission coefficient. And 0.4 is actually pretty good. I mean, that's a half, right? So this is actually really, really good. And it confirms that something that's been explicitly stated otherwise in the literature, that transition state theory can tell you something about how enzymes work. But what you need to know is what are the right coordinates to put into the transition state theory, right? So this is something that I think I was really happy to see this work, and I think it's quite nice and sets the bar quite high for what can be done in this area when you actually find the right coordinates to understand these mechanisms. By the way, they've since done the problem where the cellulose is translating through after being clipped. This comes out, and the whole strand has to move 1 notch over to be cut again, and they've solved that problem as well using the same methods. So quite exciting. A couple of other examples from the literature. This is work from the Trout group looking at a hydrolysis reaction in solution where the solvent is actually participating in the reaction. This is something very difficult to describe. You can't specify this is the solvent molecule that's going to do this, because then you lose all the entropy associated with the factorial degeneracy of transition state configurations. And they were able to actually find collective variable internal coordinate descriptions that actually do a good job of this. A couple of other problems here: diffusion in amorphous media and nucleation of hard polyhedral particles by Escobedo. So quite a few applications. What I want to do now is to demonstrate in a little more detail an example where we actually go back and we test a theory of reaction dynamics itself. Okay, so I've shown you that this can reduce dimensionality, preserve thermo, actually give you dynamics. The validation of that is that transmission coefficient being a high value. It can give you an accurate summary of the transition state ensemble and be used to go through and filter through different mechanistic hypotheses and figure out what quantitatively is the best one. What I haven't shown you is this, that you can actually test theories of reaction dynamics themselves. Okay, so this is transition state theory. I'm sure that everybody here is very familiar with transition state theory, but just to give a very brief recap, it involves 3 main assumptions. One is that you have a dividing surface that separates states in your reactant basin from states in your product basin. That's A and B. And it also assumes that the population of states on that dividing surface is in equilibrium with the population of states in basin A. Okay? And then the last assumption is that trajectories that reach this dividing surface, that is the equilibrium fraction of trajectories that are crossing through in the reactant to product direction, they never return. They continue to go on and become long-lived products. Okay? So this assumption in particular is somewhat flawed, and particularly so if you choose the wrong reaction coordinate, right? So the validity of this depends heavily on which reaction coordinate you pick. If you cut space in the wrong way, you create situations where you cross this surface, but you hadn't reached the real bottleneck, and all of those trajectories will turn around and come back. And that, of course, is a violation of this assumption. And it's also, it also gives you an error from the equilibrium probability part. That's coming from this part of the calculation. But it's well known that this is a problem, and there is a solution for this, right? So it's variational transition state theory. So formally, it's a solution to this, right? So variational transition state theory says that we should find the coordinate in the dividing surface that minimizes the transition state theory rate constant. Okay, so it is like many variational theories, variational, beautiful, and hopeless. Okay, so obviously, we've made a lot of progress in density functional theory, but this is a case where we don't really have physical principles to guide where to put these dividing surfaces. So the problem here is that this is a perfectly valid and wonderful theory, but in practice, it's been very limited. Because if you think about what goes into a calculation like this, I have to propose trial coordinates, compute the free energy landscape along those coordinates, find the bottleneck, compute the prefactor, assemble all that into this expression. For every Q, I get a rate. Notice that the rate in transition state theory is a functional, right? It's a functional of the dividing surface that you use, right? So I'm doing a free energy calculation, I'm doing a prefactor calculation, I'm multiplying those two pieces together to get a rate, and then for every different Q and every different dividing surface along that Q, I have to decide which one was the best choice by looking for the minimum along all those candidates. Okay, so a lot of work would go into doing this in practice. There are some shortcuts that have been developed by Trular and Garrett, but they are assuming a priori what is the definition of your reaction coordinate so that you reduce it to a one-dimensional problem of just deciding which slice you're going to choose. They're not truly doing a variational calculation where you vary the direction in space that you're cutting. Okay? So this is something to keep in mind, that while there are probably a lot of theories out there that would claim to have done VTST, it's a partial VTST calculation. We can't actually do the full VTST calculation for any problem of appreciable complexity yet. Okay, well, we took this procedure, likelihood maximization, and we recognized that actually, why do we ignore the velocity along the trial reaction coordinates, right? So if you think about it, that has a lot to do, if I have an inertial barrier crossing process, one where the energy landscape is smooth, and I'm a little bit to the left when I fire the trajectory, but I have enough momentum to go over the top, then I increase my probability of making it over to the other side. So you can think of that as, in a sense, something analogous to the committer. It's been around actually longer than the committer. People called it a reaction probability. And in fact, this object, this probability of reaching the product state, given a value of the coordinate and a velocity along that trial coordinate, is the thing that Kramers combines in a linear combination to develop his reduction from the two-dimensional phase space down to one and give you Kramers theory. Okay, so this is this reaction probability that we're going to use now instead of committers, and we're going to do the data collection in the same way. We do aimless shooting to get our realizations of these reaction probabilities. Same data-driven approach. We get the data first. We come up with the mechanistic hypotheses second, and then we validate the optimal combination of all of those different variables identified from the same likelihood procedure, but now applied to reaction probability outcomes that involve velocity along trial coordinates and not just positions along those trial coordinates. Okay, so all the same things we're going to be able to do, but now in addition, we can actually now effectively do variational transition state theory, right? So what this is going to do, I'm going to claim, is it's, in fact, you can see that it has to do this from the nature of the thing that you're computing. The transmission coefficient is a correlation between your velocity and the outcome of the trajectories, and that's exactly what we're building here, is a likelihood framework that maximizes that correlation, okay? So this now allows us to do variational transition state theory, but now instead of choosing the coordinates first, doing the rate calculation second, choosing the one that's the minimum rate, we actually collect the data first, investigate all the coordinates second. This is a practical way of doing variational transition state theory, and I'm going to claim that it's the first one that actually allows us to investigate however many coordinates we want to look at. Okay, so this actually, it turns out, if you apply this method and you don't have an inertial barrier crossing process, the likelihood maximization says this coefficient should be 0, and it reverts back to the original likelihood maximization procedure. Okay, so it's completely general. It works on both sides of the fence. If you don't know whether you have a process where you would best be using transition state theory, or whether you would be best using Kramers high friction model, then you can actually use this method. It not only tells you what coordinate to plug in, it tells you what theory to use that coordinate in after you find the coordinate, right? So I think that's pretty neat. And here's the example, the very simple example, just showing the results. This is a 12-dimensional model potential, a 12-dimensional bath coupled to a double well potential, a quartic double well. And what you see here are results from reaction coordinates that were generated by the original likelihood maximization procedure and reaction coordinates generated by the inertial reaction coordinate procedure. Okay, so this vertical axis is the transmission coefficient that you get. The horizontal axis is the width of the committer distribution. So in the early slides, I focused on the width of the committer. Now I'm looking at both, and what you see is that actually both get better, right? So the inertial does everything better than the original likelihood maximization procedure. It actually, every single time, gives you a transmission coefficient near 1, whereas this one also gave pretty good values of the committer distribution, but the transmission coefficients were down around 1/2, and we know that it's possible to reach near 1 for this particular problem. Okay, so inertial likelihood maximization, I think, is really, really, really quite powerful in that it sort of allows us to actually do VTST in practice now. I see people standing up, and that means I'm out of time. I won't have time to convince you that this is an interesting example problem. Ion pair dissociation, seemingly the simplest thing that you could ever study, and yet it gave people problems for a very long time. We validated these results by Geisler that show that indeed distance between the two ions is not the correct coordinate. You need some solvent coordinate to describe this process. I will very briefly go through the results to say we found the solvent coordinates that do a decent job at describing this process. They don't do a great job. But what's really interesting about this problem is that it has been the sort of example problem in a long-standing debate about the meaning of Grody-Hines theory and variational transition state theory and the relation between them. These slides will be on the web, I guess, but Grody-Hines theory is based on a generalized Langevin model. Variational transition state theory, you can always construct a harmonic bath that gives you this generalized Langevin model. And so many people have looked at these two ways of viewing the problem and said, oh, they must be the same, right? And there are two different ways of interpreting that, right? So Hines, who came up with this construction in the first place, said, but don't take it too seriously. Grody-Hines theory is more general. Some other people agreed with him and had some insightful comments there. There are very good arguments on the other side that say actually Grody-Hines theory is just a version of multidimensional transition state theory. And specifically in the context of ion pair dissociation, Trular and Garrett said if Grody-Hines theory works for a problem, and it does for ion pair dissociation, then that means that if you could do VTST perfectly, then you would not have any recrossing left. Right? So that's the sort of two ways of viewing this. This is a debate about the meaning of two reaction dynamics theories. And VTST could never be done exactly, so it could never resolve this debate. The methods that we've developed did resolve this debate. And I will leave you to go to the paper to see which camp was correct. And I think that, to sort of summarize, transition path sampling used to be thought of as a way of computing rates by throwing ropes over mountains in the dark. I think that it's a wonderful tool, but it's now much more efficient than it was before. And we now don't have to work with these random shots. We can actually find the right coordinates in a systematic way, and then go back to the more classical ways with simple theories that are based on a few physically meaningful parameters. This is related to coarse graining as well. I will skip. And I think that when you think about multi-scale modeling, I hope you will remember my talk and remember that there's a whole off-diagonal region here that belongs to the world of rare events. Okay, so this is where my group lives, and these diagrams and these coarse graining pictures always forget that if we can find the right coordinate, we don't need to go from 100,000 degrees of freedom to 10,000. We can go from 100,000 degrees of freedom to 1, right? And you get these very simple pictures. Okay, so that's my story, and I want to thank the NSF for sponsoring the work that we've done in this area. I want to thank the organizers for having me down here. It's a real honor to get to share this work with you guys, and I want to, of course, thank the people who are really integral to the ideas in this work: Ryan Mullen, Bernhard Trout, Greg Beckham, Joan Shea, Peter Bullhouse, and Brandon Knott have all made very important contributions to the things that I've shown you here. There are videos on YouTube and some scripts that you can download from the web to do these kinds of calculations. And that's it. Thank you.